So welcome everyone to episode 12 of Machine Learning at Helmholtz-Zentrum Gestacht. Today we have a really interesting paper about increasing the resolution of wind and insolation fields. This is an interesting problem with a lot of interesting applications. We're going to talk about why the authors want to do this, how they do it, and we'll talk about some of the caveats and how to really interpret the results of these techniques, which really create data where you previously didn't have it. I'm here now for the first seminar where I actually have an in-person component. I'm here with Marcel Nonnenmacher and Tobias Machnitzki, who's just joined our group as a PhD student. So welcome, Tobias.
Yeah, hi, thank you very much, David.
I think we'll hopefully get you to do a better introduction after people come back from this heavy summer vacation time. So what you're seeing now is this PNAS paper, Stengel et al. And what they're trying to do is take input data, which could come either from high resolution data sets we'll talk about in a minute, or from a climate model. And they want to take these fields of wind speed in the horizontal and vertical direction, or they want to take fields of direct and indirect sunlight and increase the resolution by a factor of 25 or 50. So in principle, this is an impossible problem, right? If you have data which is kind of averaged every 100 kilometers and you want the same data every 4 kilometers, there's many different versions of the high resolution data which are consistent with your observed low resolution data. But the reason they can do this is because it's not just some arbitrary data, it's rather a specific kind of phenomenon that recurs, that has statistical patterns, and they're able to get supervised labeled data, labeled data for supervised learning, where they know the correct result of the resolution increase in some cases, and they can train the neural network to produce the correct high resolution output from the low resolution input. And this general problem is called superresolution, taking an image and increasing the resolution that you have. So we'll go over a little bit about what they're trying to do, what are the actual fields they're trying to reconstruct, and what are their techniques. So for training these networks, they have, we'll start with the wind. You have horizontal and vertical, or rather meridional and zonal wind fields. In the high resolution data set that they use, these winds are on a 2-kilometer grid. And what they're going to do is they're going to, you can see this in figure 1, they're going to take this high resolution data, they're going to coarsen it, essentially reduce the resolution of the data, and then they're going to train the network to go back to the original high resolution data. And then having trained this on their high resolution data, which is based on real world observations and some kind of additional data processing procedures, then the idea is you can apply the same network to runs from a climate model. And in particular, they're interested in a scenario with a 1% CO2 increase per year. So the idea is having trained it on the real world to apply it in some future scenario to get a higher resolution field than you could afford to compute in your climate model. And why do you want this high resolution field, especially for wind and sunlight? Well, one of the reasons is indeed where to put your wind farm, where to put your solar panels. What are going to be the impacts of various weather phenomena is an interesting question as well. But in order to plan effectively, to make policy decisions, you need to have a reasonably high resolution map of where things are going to go. And that's exactly what you can't get from the climate models that we're capable of running into the future. They just don't have the spatial resolution that we need. Okay, and so the data they're training on, we have this wind toolkit and this National Solar Radiation Database as well. We have, grid sizes on the order of 2 to 4 kilometers. We have recent years, we have a lot of these images, some 30 to 50,000. And then we're going to reserve a few of them for testing as well. The idea is, having trained on a majority of these images, you hold out a few for testing, as we often have. So the framework they use to increase the resolution of these images is rather similar to what we saw in several previous, in particular in, I believe it was episode 5, Real Fake Clouds, where they use this generative adversarial network, in that case, to produce satellite images of clouds from meteorological fields. But the same principle is used. The neural network, given the low resolution image, is going to output a high resolution one, and then a second neural network, a discriminator network, is going to identify whether the high resolution image came from the neural network or whether it came from the original training data set. So the generator network is trained to produce high resolution images which are indistinguishable from the high resolution images in the training data. The discriminator network is trained to tell them apart. So they're adversaries, and this is an adversarial learning scheme. We covered in the previous episode the equations that define the training losses for these two adversaries. I don't think we have to go over them again right now, but it's all there if we want to have a look. And if we have any questions, we can jump into that as well. And so in figure 3, we're seeing different possible approaches to increasing the resolution of these images. On the left column, you have the low resolution inputs here for the zonal meridional wind fields. And you can see the speed in meters per second over here. The simplest thing you could do is just interpolate with a non-trained standard, in this case, a bicubic interpolation. So you have some mathematical formula where you kind of smooth out based on the neighboring pixels. And you get something which is consistent in that it produces the same average values if you go back to the low resolution, more or less. But all the high frequency information is lost. If we go to the ground truth wind data that this was trained on, we can see all these ripples, all these fine features are completely lost in the bicubic interpolation. The next thing they try is just a convolutional neural network, which simply tries to match in least squares the ground truth from the low resolution input. So it tries to get the average, because it's using least squares loss, essentially tries to get the average high resolution image. But this also turns out to be blurry, perhaps because the distribution of possible images, probability distribution is broad, and we're taking an average, so it becomes blurry. And then they use a GAN. So this is where their neural network has been trained not only to match the ground truth, is what they call their content loss, which was the same in the Isola et al. Pix-to-Pix framework that we discussed in episode 5, but it also fools the discriminator. So the discriminator network can't tell apart the GAN-generated super resolution images from the ground truth images used in training. And you can see then they're not identical by any means, but they sort of have a similar texture. They look like the same kind of images. So this is how they do this for the wind fields, and they're able to go from low to high resolution. So, okay, a natural question to ask, and I think with something we've discussed as well, is does this really mean something, or are we just making up a pretty picture which is sort of consistent in the average with our low resolution stuff? And one of the ways they check this is to look at some physical characteristics of these wind fields and say, are they consistent with what we know about wind? So one thing they look at is this energy spectrum. If you look at the kinetic energy at different frequencies, spatial frequencies or different wave numbers, you get this spectrum, which was not something the network was specifically trained on. And we can ask if this is correct, if it's physically consistent. So the ground truth data is in black. We have this curve, you have this decrease in energy as a function of wave number, and then at very high wave numbers, there's very high spatial frequencies, it sort of drops off. And you can ask, do the images, the wind fields produced by the super resolution network, do they actually capture these statistics? And if we look at, for example, the bicubic interpolation, where all these fine features are lost, this appears in blue here, we see we really don't have the same spectrum. If we go to the CNN, which was trained by least squares matching to the high resolution images, we get slightly closer. And we get even closer when we use the GAN. So we're better, although not perfect, at capturing the energy spectrum of the wind fields. The other thing they look at is, if you look at the gradient in the wind velocity over space, what is the probability distribution over that? And again, we can look at the low resolution inputs themselves, we can look at cubic interpolation, and then we can look at the CNN deterministic, the least squares as well as the GAN fit. And we see we're getting closer and closer to this distribution. So I don't know, maybe someone more who has more expertise in wind fields can speak to this, but at least they're claiming this is a reasonable physical check that the images, the wind fields output by this method, when we increase from low to high resolution on this wind data set, this wind product, are physically reasonable. They then test the robustness of the method with respect to noise. We're saying if we add a little bit of noise to low resolution inputs, what happens to the outputs? We see changes in the mean output. So we have a bias when we add noise. And then we also see a variation in the output, which is interesting that you have some regions where the output is actually quite high velocities. And then you have actually very high variance as well. Other regions where it's high velocity, but the variance isn't so high. In any case, what it shows is that you get reasonably similar outputs for the same input. So it's not like it's just going to generate completely random stuff that's going to be different every time. It is a good point to mention that whereas GANs generally try to describe the probability distribution of the output given the input, this method is more or less deterministic, that at least after training, the generator will always produce the same super resolution image for the same low resolution input. So a lot of GANs, including the pix-to-pix GAN we covered in the past, will produce distributions over outputs given the input. This is not the case at present. It's really just a deterministic mapping. So this has all been done on the training data. They can then go and look at climate model simulations. So this is quite a jump. It's a jump in terms of the kind of data that's going in. Previously, it was the exact same data, basically used as input and output. It just took the high resolution ground truth output from the this wind product, the Wind Integration National Database. It's one of these recursive acronyms like GNU, but they took this high resolution data and they just took every nth pixel. And then this gives them low resolution inputs. So they want to reconstruct this from a subset of its own pixels, essentially. Now they're doing something completely different. They're going to a whole different data set. And they're putting in much, much larger inputs. Before they were training it on these relatively small images, I don't know if they have scale bars, but you can see this. There's not too much of the globe right here. I believe it's 500 by 500 pixels. Is that right?
For the output, yes.
For the output, and they're what for the wind, they're 2 kilometers each, right? So we're talking about 1,000 kilometers, 5,000 kilometers roughly. Whereas here now we're actually running it on the whole globe. And at first thought, how is that possible? We're training it on one image size and we're using it on another. But this is one of the nice things about using convolutional networks. If every part of your network is just consisting of convolutional filters and nonlinearities that are applied pointwise, you can actually run it on any size input, not only the one that you trained it on. So this allows them to run it on these much bigger images, which are now really covering the entire globe by longitude and then plus or minus 60 degrees by latitude. And this goes back to episode 2, right? The question of what happens in the sphere. We're using convolutions, which say, look, this many pixels to the left, right, up, down, in this case, longitude and latitude and longitudinal axes. But the actual distances physically that corresponds to are going to vary by latitude quite a bit. And they're not doing anything like spherical convolutions or cubed sphere transformations or anything like that to account for this, which is why it doesn't work so well near the poles. And they mentioned that you could look at different projections, and perhaps you could even look at some of the convolutional filtering techniques we used in episode 2, and then maybe you could apply this to the whole Earth. But again, okay, without getting too deep into how to interpret this stuff and what do we believe, what do we not believe, just in terms of the workflow, here, the true high resolution field is unknown. All we have is the low resolution field from the climate model simulation. And again, this is a simulation, I believe, from 2020 to 2039, if I'm not mistaken, with a 1% CO2 increase per year. Yeah, correct me if I'm wrong on that. And we have this low resolution, I think about 100 kilometers a pixel of the equator. We run the algorithm that was trained on the 2007 to 2013 wind fields to produce a high resolution 2 by 2 kilometer resolution wind field. And then we're able to get that over the entire globe. And the idea being then, because we can apply this to climate models running different scenarios, we can then really get high resolution, and one would hope accurate estimates of local conditions in the future, conditioned on whatever forcing we have in our climate model, which would allow us to plan our wind farms, our solar panels, or whatever else we want to plan. So I don't know, maybe this is a good point to open up discussion a little bit before we move on, both in terms of the workflow, what they're doing, does it make sense to everyone, are there questions on that, as well as what do we think about training on these past wind field data and then applying it to these climate model simulations? Is it a reasonable thing to do or not? I'd be curious what people think in the chat. As well as you guys in person, how do we evaluate this? So under what conditions would we expect this generalization to work?
Well, the first thing you would probably want to verify is that the distribution of the inputs that you get from the global circulation model is really similar to the distribution of the inputs that you got from these other two data sets that you were working with.
Right. So you're saying the statistics of what's going in should be the same as the training data. I mean, this is generally a good principle for a neural network, right? If you train it on one thing and test it on another. Now, of course, the whole image doesn't have to be the same, but the input patches of the size which get processed all together, right? So each output pixel, we're going 512 by 512 output pixels, and then we're increasing by a factor for the wind of about 50, right? So we're starting with roughly, it looks like about 10 by 10, if I count the pixels in figure 6 lower. So basically this 10 by 10 patches should match the 10 by 10 patches of input from our wind product that we trained on. Now, this is a much milder requirement than saying that the entire input image should match, but it's still a requirement. And in a way, it's difficult to imagine it will always be met if the climate model really describes a drastically different scenario than what we had from 2007 to 2013, then perhaps the wind fields may be very different, but they may also not. It may be that certain events become more rare, but they're at least still represented sometime in the training data set so that the two distributions overlap at least somewhat. That the events that happen in the climate model always happen at least once in a while. But this is an empirical question, and as far as I can tell, they haven't really addressed it, have they?
I didn't see anything. It would be easily doable. You could just check for every data point from the climate model if it's an outlier respective to the distribution of data that they use.
Yeah, I mean, and how to do that is not trivial, right? Like you're talking about a 100-dimensional image space, right? 10 by 10 images. So you have to, it's not trivial to say, is this point an outlier? But there are ways of doing it. You can look at distance to the nearest point by some metric. You can fit a probability distribution to it, even again. And yeah, so this might be an interesting thing to check. And then the physical constraints or the physical checks they did, right? So I believe, let me see if I can find this. When describing the results in the wind data, they mention, I believe, that they did repeat these tests of the kinetic energy spectrum with respect for the climate data. It also had the correct spectrum of energy at various wave numbers, but they don't actually show all this. Here we go. Although not shown here, the energy spectra and velocity gradients for the global SR field also show the correct turbulent flow characteristics. That's a pretty big statement. I mean, it's encouraging they have thought of it and there's something to do there. But I think this is a general question. And it's not clear to me, if you try this and you show it some new input data that's too different and it goes horribly wrong and it gives you nonsense, how do you know exactly? I mean, yes, you can do physical checks if you know what to look for. But it's tricky. They don't have really such a physical check for the radiation. Oh, we have a question or a comment from the Zoom group chat. What about the selection of test images right out of the frames the model is trained on? First pointed out by Caroline. Shouldn't they at least have made the test set out of images from the end of the time series? Okay, there's a couple things here worth mentioning. So they do some testing on held out data from the wind, high resolution wind data set that they didn't train on. And I believe whenever they report root mean square error in these tables, they are showing held out test data. But then there's an interesting point raised: is it all mixed in? Should one really not hold out a whole year and not only randomly interspersed, randomly selected time points from the same time period? Because it may be that it's much easier if you already have neighboring time points, right? You know, if you have May 24th, 2012, it may be a lot easier to predict May 25th, 2012, because you'll have sort of the same set of statistical patterns because there are some weather and climatic variables which change more slowly. But did they do that? When they did testing, did they hold out the training data? I don't know. I don't know if somebody's caught this. I believe they say they held out a certain number. Approximately 10% of the training examples are held out for validation in each case, these characteristics. But do they hold out a particular time period? This is a question I don't know the answer to. I guess we could ask the authors, but this is a very good point. Because indeed they're asking, even if the climate model really did have the right statistics, it may be that just by doing different years than the training data, that there's too much variability from year to year, and that is very difficult with only 6 years of training data to do other years, which may have different weather and climate dynamics. Okay, that's a very good point. Thanks, Felix. So this is all the case for the wind data. They also do the same thing for insolation, for the amount of solar radiation falling at the Earth's surface over space. There they have a slightly lower resolution data, so they're only going from, I think, about 100 kilometers by 100 kilometers to 4 by 4. But it's all the same principle, right? We have our low resolution inputs, we have our ground truth, and we're getting these maps of radiation. just as they have two channels for wind, the zonal and meridional wind speeds, we also have two channels here. We have, and again, correct me if someone is maybe more of an expert on this terminology than I am. We have this, the DNI is direct radiation, which is falling, direct sunlight, which is hitting, which would be hitting a surface which is held orthogonal to the sun's rays. And then you have the diffuse horizontal incidence, which is illumination, which is basically light which has been scattered and reflected, which comes from every single angle, essentially, more or less equally. So these are two different kinds of radiation. They'd both be important for deciding where to put your solar panels or solar heating facilities and so on. So there are these two channels we want to predict, and they're predicted together, just like the horizontal meridional wind fields are not that independently. So I think this is also, is there anything else you want to say about the radiation in particular? The only thing I would mention, and again, if someone is more of an expert and wants to chime in, that would be great. When they do the training from this high resolution data set, which is essentially something like, not exactly a reanalysis product, but it's sensors with a bit of processing. But then they apply it to climate model data. And then they have to do a bit of a trick here to get it to work on the climate model data. They look at the lowest fields, they look at the radiation coming through, and what they get is the global horizontal irradiance, and from this they want to calculate these two fields, and they have to use an algorithm described in reference 46, the direct insolation simulation code, and this should then allow them to calculate, starting from just the one field from the climate model, they're able to calculate these two radiation fields. Calculate one rather, and then the other they can calculate using Formula 1. Which means if this algorithm is accurate, that's great. If it introduces any additional errors, then these will be present when applied to climate model data, but not in the original training. And there's no real obvious way of detecting those errors in this workflow. But okay, they do this for the radiation as well in more or less the same way. I think it's also maybe worth mentioning some of the differences from the previous conditional GANs we looked at. So in a previous episode, we also looked at a conditional generator which said, give me an input and then produce an output. And then the discriminator, in this case, which is producing satellite images of clouds from meteorological fields, it would also take the same input and it would look at the output and say, is this a real high resolution image from our training data, or is it a fake image that was generated by our generator? And it tries to distinguish them. So basically it says, given the input, was this a real or a fake output? Here, the scenario is different. The generator is the same. It takes a low resolution input and produces a high resolution output, whereas before it was taking meteorological fields and producing clouds. The discriminator now only has access to the output, not to the input. So it's not trying to say, is this a consistent output given this input? It's just going to say, is this consistent as a potential high resolution image? It's actually solving a rather much easier problem. The overall distribution of generated versus high resolution images, as opposed to each distribution conditioned on a particular low resolution input. Both ISILA 2016, which we considered, I believe, in episode 5 as well. And this present paper, they, in addition to the GAN loss, they had an additional supervised content loss. So it may not matter so much, but it's a major difference. Another difference was in the architecture. When we look at how these networks are built, we won't go into them too heavily here. We can just briefly pull it up in the SRGAN paper that they based their architecture out of. In the PIX-to-PIX scenario, you have a UNet where the resolution decreases down to nothing and then back up to the original image size. Here, the resolution is constant through all the different layers of the network until you get to the end, in which case it gets increased for this SRGAN by a factor of 4, although for the present paper by a factor of 100. And then the discriminator is reducing the image size at every stage, essentially. So the architectures are different, the loss is different, but in the end, we're learning another image-to-image translation task. Okay, so we have this framework applied to wind and to radiation fields. For the radiation fields, they don't have the same physical checks in terms of turbulent, in terms of kinetic energy spectra, where they even have formulas to compare to. What they do have is something else, which they call the semi-variogram, where they ask, if you look in circular regions of a given size, on average, how much variation is there in the field, in the radiation field? And if you look in the ground truth data, the high resolution data from 2007 to 2013, and of course, as you see, as the region becomes larger, then the normalized variance gets higher and higher. And it follows a particular statistical pattern, but it actually stays reasonably high even for very small regions, because even at the smallest lag distances, so the smallest sizes of the circle, maybe 5 kilometers, you can still have a cloud over half of that region. So the variance doesn't go to 0. Whereas if you take something like the cubic interpolation, which really just makes everything way too smooth, then the variance will be much less over small regions. And that's exactly what you see here, that the bicubic interpolation really underestimates the variance in small regions. A CNN convolutional network trained on least squares does better, and the GAN does better still, although just like the kinetic energy spectrum, it doesn't work perfectly. But we're seeing that the statistics sort of match the original high resolution data a little bit better. So this is another statistical check. It's not quite as based on physical principles, but we can ask, do the statistics of the fields produced by this method match the statistics of our training data? So that's basically it. They train on these high resolution products, and then they can basically increase the resolution of the climate model outputs. I think there's a lot more to say, a lot more potential questions to ask, but let me just open it up to discussion right now. What do people think? What's clear, what's not clear, what's interesting? There is another question already in Zoom chat from Carolyn Arnold at DKRZ. How about the energy conservation in Figure 9? How about it? Yes. Resolution to match the pixels in the low-res image, the DNI would be larger than the values shown in the inset ACCSM. In that respect, the GANs perform a lot better in Figure 7. I'm not fully sure I understand the question. Carolyn, if you want to jump into the Zoom chat on voice, you can maybe explain a little more what you mean.
Hi, can you hear me?
Yeah.
Yeah, maybe it's easier if I explain it this way. So when you look at the two insets, specifically at the upper right corner, there is very well visible. And now imagine you average the top right of the super resolution image. It should give a value like 900 watts per square meter. But when you look at the low resolution image, you have very low ENI actually in that region. So somehow the super resolution seems to increase all the values.
That is quite right. Yeah, I think that's a very reasonable concern. Presumably, I would be surprised if it had a global bias overall. I think it should be pretty easy for the network to learn the right average, and on average, it should be the same. But in particular cases, yeah, it really, in this case, it doesn't seem to average back to the original result. And interestingly enough, I mean, yeah, we don't have, I mean, you mentioned that in figure 7, it did a lot better. Yeah, and it looks pretty similar units. Like if you average the high resolution thing, you get something a lot like the low resolution thing. Whereas it's not happening here. It's quite interesting. And yet it should have been pretty straightforward to impose this constraint, right? Could you imagine modifying the loss maybe to, so I mean, part of the problem is indeed these are out of sample inputs, right? Presumably if they look more like the training data, we would have had better energy conservation, but not only are they getting what's clearly the wrong answer, yeah, exactly, as Felix points out in the chat, in figure 7 is training data, where they know the ground truth, and they have this, you know, supervised, it's not?
Figure 7, I think, is also on the global circulation model.
The comparison of various SR methods.
Oh, okay, sorry.
Yeah, figure 7 does seem to be, right, so you have this, you have both the GAN loss, the need to pull the discriminator, as well as a content loss needs to match the high resolution, the true high resolution data in least squares is going to enforce this. But one would like to have here is a network where the output should match the input in terms of the average. I mean, I guess it's also a question of interpretation, right? For insulation in a climate model, see, in a climate model, when you think of the value at a grid point, you like to think of it as an average over that region. Certainly for something like radiation balance. For wind speed, maybe it's slightly more complicated, but basically the same. But when they went from high to low resolution to do training, did they average or did they just take every nth pixel?
No, they averaged.
They did average. Mm-hmm. So in this case, well, yeah, it just didn't work, huh?
And this could go wrong at a bunch of different steps, but it might be that the training loss didn't go to 0 because maybe the network isn't complex enough. It could be, as you said, that it's an out of sample data point.
Well, wouldn't it be so simple to just calculate at the end of your, when your network outputs a high resolution image, to have one more layer and have that layer basically calculate the mismatch between the average of the high resolution output and the low resolution input, which you certainly know during training, both of those, and just add that back on.
Yeah.
It would potentially introduce some sharp boundaries and discontinuities, but you could smooth those if you wanted to. It just doesn't seem that difficult to fix this issue.
So I'm not sure how big of an issue it is across all different spaces. We've seen this one inset where it seems to be problematic. But in principle, yes. This goes a bit into the direction of the original SRGAN paper, where they didn't have a mean squared error as content loss, but they added these BGG feature functions. And you could have not only these feature functions from BGG, but you could add any desired feature over the high resolution image. And one of those could be, in fact, as you said, just apply an average Boolean and then do a Euclidean distance over these features.
You could, oh, I see, that's very interesting. Yeah.
Just like you put in equation 5 that you just put on. And these feature functions, phi, ij.
Yeah.
In this case, these were like the features that the neural network learned while it was learning to classify some natural images. But you could just say, let this be the exact same operator that they used to go from high resolution to low resolution when they actually created the training data set.
Yeah, it's a very nice idea. It would have cost them basically nothing, huh?
But one more term on a loss.
Yeah, or maybe they tried it and it didn't work. For some reason we can't fathom, as often happens in machine learning. Very good, seemingly good ideas don't work for inexplicable reasons. But potentially this would be a pretty easy thing to do. Download their code, change a few lines, and suddenly you could get you know, the correct energy balance in your outputs, regardless of, even if you go way outside of your training data, you may get the wrong answer, but it should still match the low resolution energy.
I mean, you could quantify how much it doesn't, because by the end of training, it would be exactly that loss term. How much bigger it is from zero.
You could build into the loss, or you could build a hard constraint, which simply makes the network incapable of modifying the average energy. But in any case, these are, yeah, that's a really good point, Caroline. Any other questions? I don't know if anybody's looking at the YouTube chat. I'm going to open it without trying not to create a audio feedback loop. Yeah, so do we have any chat questions here? Doesn't look like it. So I have a couple other questions. I'm hoping we'll get a few more from the other participants, but I mean, something that, questions, comments, I'm wondering if these results are temporally coherent, right? So if you were to apply this to each state of the climate model one at a time, you know, and if the climate model is producing an output, depending whether you save it once every 30 minutes or once every day, if you watch the video, it looks coherent. You can see weather patterns move and swirl and change. If you were to do this, would you see something coherent, or would the high resolution features that are sort of imagined by the network, by the generator, in order to match the statistics of the training data, would they just kind of jump around completely insanely from one time point to the next? It's a little unclear. It might not be so bad because it is deterministic and it is somewhat robust to noise, as they show, but there's no real guarantee that it'll be temporally coherent, and I wonder if it would be. Another thing I'm wondering is, you know, especially for the high resolution wind fields, and I think, are these surface wind fields? I'm trying to remember.
I think they were the 100 meters.
100 meters. So at 100 meters still, I think the land use and orography, you know, all the terrain information would probably provide you some good information. You could provide, you know, land use information like where's a farm, where's a forest, where's a city, as well as a terrain map as a static input to either the generator or the discriminator or both. And you might find improved performance. I think you could probably get a better estimate of what a high resolution wind patterns will be if you know what the terrain is. So this might be an interesting extension as well. Of course, this isn't only about orography. If you look at other climate variables at low resolution that you may have in the climate model, you may have, in addition to the wind speeds and radiation fields, you've got temperature, you've got pressure, you've got moisture. All of these may provide additional information about the wind fields you're trying to do super resolution on. So providing them as extra inputs to the network might not be such a crazy idea. Of course, as you provide more and more inputs, you involve more and more parameters, and you may need more and more data then to avoid overfitting, but it's a possibility. And then I guess one thing we just didn't touch on, but is sort of interesting, is they don't go from the directly to the high resolution from the low resolution. They have this intermediate step of medium resolution, and they train two different generator networks to go one step at a time. And I think this allows them to limit the depth of the network, which they claim makes it easier to train. This is kind of an unusual move, and it might lead to a less than optimal for more performance, but it might actually really maybe help with speed memory during training, I'm not sure. As a result, they get as outputs a medium resolution and a high resolution image. I'm not sure it matters too much in the end.
I mean, one thing they could have done once they trained both of them individually, they could have just taken gradients through both of them in one go and see if they could still improve it or not.
Yeah, it would take even just gradients with one while the other is fixed. You can see, yeah, right. So given the mapping of, say, low to medium, can you improve medium to high with that mapping in mind, and vice versa, or improve it all together? Yeah. When they're doing things quite differently than SRGAN, and then SRGAN is really only increasing things by a factor of 4, and they are going with a factor of 25 or 50. So I guess they're just using more layers.
I mean, in a sense, they're using exactly twice as many because they take 2 times the same architecture and one goes from
right. So say we're going in the case of radiation, they were doing like only 50 times. So that means you're going roughly 7 times and 7 times, huh?
I think it's one is doing 5 times and the other is doing 10. I'm trying to.
Oh, okay. And they do this, so if you look in the original SRGAN, everything stays the same size in the generator except till the last few layers. The second to last and third to last layers increase the resolution by a factor of 2. I don't know if they just stack more of these on or if they have additional residual blocks in between.
We could look at the code. So for both papers, there's actually code on GitHub.
Okay. Yeah. Something I find very nice about this is like a potential little quick project to try out is that, yeah, the code's available and some of the ideas for potential improvements are really probably just a few lines. And it seemed, I think, to have trained this on just a single GPU, it takes a while, especially for the medium resolution to high resolution, maybe a better part of a week, but it's something one could do. Another question from Zoom chat. What about the heavy pre-training with MSE for 2000 epochs? It seems to give the network a strong prior on MSE results for later GAN fine-tuning. Maybe that also enables a high jump in resolution. Right. So what Felix is referring to is, in the beginning, is they train only in least squares, just as if they were only doing a CNN super resolution net without any discriminator, without the adversarial network framework. And then only later they add in the additional terms. And yeah, so it may be that if they didn't do this, it would have a different result, and this is particularly tuned to the least squares fit. And then maybe he says this could enable the high jump in resolution if possible. Yeah, this stuff is worth exploring. So because it's all deterministic, I think it's a little sad actually when you can't get the probability distribution of multiple possible high resolution images which are consistent, A, with your low resolution input, and B, with your training data. So it would be nice to know, okay, if I look at this spot and I want with 2 kilometer resolution in my, in 10 years, in 2030, in my 1% per year CO2 scenario, what are my wind fields going to be? What are my radiation fields going to be? It would be nice if I could, instead of just producing a single deterministic output from my super resolution, I could actually draw multiple samples. And you pointed this out in a previous discussion, Marcel, right?
If you look at if you can quickly open the SRGAN paper,
yeah,
I think it was the third figure one about this.
53.
Where they visually show, yeah, exactly this one. So they kind of nicely give you this high-level impression of what the different loss terms do. So for a given low-resolution image patch, there might be a lot of high-resolution ones that are kind of consistent with it. I think if I understand this, if I remember this figure correctly, it's all the red ones. And the mean squared error one gives you kind of the mean of those. So this is why they argue if they combine the mean squared error loss with a GAN loss, what they will find is the yellow the yellow instantiation of those high resolution images that would be consistent. Now, a pure conditionally trained GAN would give you something that's stochastic. It would give you a distribution. It would give you the distribution of all the red squares. What this whole method gives you, just to maybe just restate what David just said, it gives you this one drop, this one yellow one. And it's not entirely clear how going from purely MSE loss to MSE plus the GAN type loss, which of these red ones actually is picked for the yellow one.
Yeah.
So what you could do if you would have a stochastic output and you have a lot of these 100 by 100 kilometer resolution maps, and then you go to 2 by 2 kilometer resolution, what you really want to have is you want to have high reliance over the value at one of these 2 by 2 kilometer resolution pixels, because as the introduction of the paper argues, 2 by 2 resolution really matters for the positioning of, say, a windmill. But if the value at that 2 by 2 resolution pixel could be very different across these different instantiations, these different red squares in figure 3, it would be really cool to see in how many of these this 1 2 by 2 kilometer pixel is actually still a favorable spot for a windmill. So you would want to gather a lot of statistics, but with this method, which just in a mysterious way picks one of these to be the yellow square, that it actually, this thing becomes very tricky.
Mm-hmm.
So this is actually discussed by the authors of the PNAS paper in future work. But at least with the current method, I think this will be hard to address. If you went back to an actual conditional GAN that actually has stochastic output, as we said, you could try to gather statistics for every of these high resolution 2 by 2 kilometer pixels. But right now, this seems difficult.
Yeah, I mean, I think as a general thing about conditional GANs for images, I mean, okay, ISILA 2016, which we covered in Real Fake Clouds, they do show samples in the supplementary figures, right? They do show multiple realizations of, I think they're doing image-to-image translation, and one of those translation tasks actually is super resolution, if I recall. But, I mean, yeah, they show visually you can get some variation, it looks nice, but I don't think anyone's ever claimed to have a GAN which really shows kind of the correct, if you like, I don't want to say posterior distribution, but really captures the full range of consistent possible inputs that might have occurred in the training set. I think capturing the full variability of possibilities is still a very difficult and mostly unsolved problem for these GANs.
If I remember, I saw that correctly, I think they even made a statement that the conditional distribution, so the set of all the consistent images in high res that you could produce for a given low res one, that the uncertainty of these is underestimated.
Yeah, but then they're still using a content loss term, right? They're still using an L1 loss in addition to their condition. They do show some images where they throw that out. They only do a conditional GAN term, right? And they provide the input image to the discriminator, so it's conditional densities all the way. And in theory, that's a classical conditional GAN with no other, weirdness in the objective function. And in principle, that could learn the full thing. But in fact, none of the samples look good then. And they're trying to like give you a picture of a road from a segmented picture of a road, and it just doesn't even look like that you have pedestrians without legs and cars with no fronts. And so I don't know, maybe the problem is networks, maybe the problem is training. Getting the full variability seems out of reach, but I mean, at least in some simple way, one should be able to estimate the how good are our uncertainty estimates. Maybe if you just look at the standard deviation for each pixel, and then look at the residual from the mean to ground truth, do those things tend to have the same scale? Are our standard deviations roughly good? If we take nonlinear functions of maybe that are related to our domain, right? So if we were able to run this on a whole time series of images, and we want to know, okay, well, what is my nonlinear function? But what is my power output in July going to be if I put my windmill here, right? And then I can say, what is the actual value of that in my high resolution data, and what is the range of values that I predict from my GAN? from my multiple GAN samples, then is the true value somewhere in the middle of that distribution? Is it not too far out in the tails? Is it not, are we identifying the realms of possibility correctly? It would be possible to pursue this maybe, maybe in a more targeted way. And what you were saying about, Marcel, about building the downsampling into the objective function, right? Instead of just using the activations in some image classifier and saying that those should match the training data, one could then also maybe do something specific to the application, right? If you had some way of capturing some functions, maybe nonlinear functions related to power output or other kind of impact variables, maybe you could try to target your loss function to these. I don't know. Felix mentions maybe something like a pixel RNN network. That's interesting. Pixel RNN is an autoregressive method. So basically, it can generate stochastic outputs given inputs. And it generates each pixel one at a time given the previous pixels. So it kind of fills in the image. And they actually tend to fit data very well. I don't know if they've been used much for super resolution, but the difficulty here might be that, I mean, this was already taking like 5 days to train on 10 by 10 input images. And pixel RNNs are slow. Autoregressive models are slow because you have all these amazing GPUs and farms of GPUs that actually generate insane amounts of heat and do trillions of computations. But the problem is with pixel RNNs, it's difficult to exploit that computational power very well, precisely because of this autoregressive structure, because you do have to either calculate the probability or sample and generate one pixel at a time. And whereas where these GANs, because they're convolutional networks, they operate on the whole image at once, so they can saturate the computational power of all these 2,500 processors in my GPU or my multiple GPUs. So I think there'll be real computational problems with the pixel RNN, but maybe that could be a starting point for some strategy, which might work here. I'm now just thinking in general, have autoregressive models been used for super resolution? And I don't know the answer to that question. If so, I would expect that it'd rather be the 4 times, increase each resolution by 2 rather than by 50. Okay. Any other questions? Any other comments? I think we may be right now in Hamburg living in some kind of, network error where someone accidentally increased the radiation while upsampling the past few days. Let me check the YouTube comments one more time, although I've been yeah, we haven't had too many YouTube comments, but I can kind of understand that because of this 2-minute delay. And I guess finally, we'll just mention, without really discussing it too much, this blog post will be linked in the announcement email. It should be in the YouTube description as well. These GANs are trained for super resolution. And this is kind of the issue we're worried about a little bit with training on 2007 to 2013 processed observations and then running on a climate model in a different scenario with presumably different physics in the real world as well, is that you make assumptions that your test case is like your training case, and then this can lead to all kinds of biases. Here, for example, this is a this is a concern that these GAN networks can introduce racial bias. You put in a pixelated pixel of Barack Obama, and you get someone looking very different out. And this blog post just kind of, it goes through these different examples. Some of them are quite amusing, and it discusses, okay, is it a problem with the training data? Is it a problem with the network itself? And yeah, there's some really quite amusing things to look at here. So I guess we'll close with that. No more questions. Thanks everyone who joined this week. And in 2 weeks, I will send the email out now, but I can announce it right now. We will have a return to the program of Stefan Rasp from Technical University of Munich, who is going to present his weather bench paper, which basically compares data-driven and physics-driven weather prediction. And he's going to show some really interesting results, and I'm quite excited about that, and more details to follow. So thanks everyone for joining.